Hello class, time for another lecture. We're still talking about sound isolation. The first subject of this one will be composite transmission loss. So we studied transmission loss. We should have a pretty good idea of what that is. Composite transmission loss is what we need to do, say if we have a partition that's made up of different elements. Like the stuff we learned prior to this would just be, say we have one concrete wall, or we have one insulated metal panel wall. Now, say it's more of an architectural type of thing where you have a wall that has a door and a window, or maybe a louver, like a transfer duct for an HVAC system that would essentially just an opening with a grill over it. So how to account for all of those together? That's what we're going to deal with here. And then we're going to use that for the second subject of this is going to be noise reduction. So we'll use these predictions of what the composite transmission loss is to determine what the sound will be in a receiving space based on a noise in a source space. That's the big picture. First, let's start with composite transmission loss. So the definition here, probably what I just said, is overall sound insulation of a system made up of multiple components of varying transmission loss. So remember that our transmission loss was equal to 10 times log base 10 of 1 over tau, which is the transmission coefficient. We want transmission, so this will be the transmission loss of the composite wall, so long as we can put a transmission coefficient in that accounts for all components. And that's where this equation comes in to play. So the transmission coefficient of the composite wall is going to be the sum of the individual transmission coefficients times their area divided by the total area. So if we have the wall making up most of the area, that would be tau 1 and S1. It'd be whatever the transmission coefficient is for that assembly, and then whatever the area is of that wall minus whatever the other components are. So we take the door out of it, we take the window out of it. We would add that then to the transmission coefficient for the door times its area. Say it's a 30-inch door, 7 foot tall, or 70 inches tall. It's a common door size. Then similarly, transmission coefficient for a window and the area of the window, and then so on for whatever components you have. Here we're going to look at an example of how to calculate this. So we have a concrete wall. It's 4 meters high by 10 meters long. It contains a window, a door, and a louver, just like I said in my intro. We have the dimensions for each of those. And we are supposed to calculate the composite transmission loss at 500 hertz if the transmission loss in decibels for each of those 4 components at 500 hertz are these values here. So the wall is 40 decibels transmission loss, the window is 24 decibels transmission loss, the door is 20 decibels transmission loss, and the louver is not providing any transmission loss. It's basically just an open space. It's letting the air go through, the sound go through. So to solve this, we need that equation, the one we just learned. So from this info up here, we're going to be able, including this up here, we're going to be able to get all the areas. The total area is just going to be the entire 4 meters high by 10 meters long. And then the area we're going to have we're going to need to calculate the transmission coefficient for each of these. And then we're going to need to determine the area of each of these. So we'll calculate this, calculate this, calculate this, subtract those from this. So let's see that. So here we get the area. It's probably better, this one would be last. So we do the window first. 1.5 meter times 1.5 meter is 2.25 meters squared. 1 meter by 2.5 meters for the door is 2.5 meters squared. And 0.5 meters high by 1.5 meters long is the louver. So that's 0.75 meters squared. If we sum all of these up and we subtract them from the 40 meters, then we would get this 34.5. That's going to be for the concrete portion of the wall. So we have all of these, and if we sum them up, we would have this. We just need these transmission coefficients. So remember that equation was the transmission loss equals 10 times log 10 of 1 over tau. So here we brought the 10 over to this side. We're after this transmission coefficient. So then we just use the logarithmic identity. So the base to the y, so 10 to this equals the x, right? Log bx equals y, so b to the y equals x, that identity. So now all we have to do, we can just rearrange these. So we're calculating for tau. And then we just have to plug each of these transmission losses in here. And we would get these transmission coefficients. And we can multiply each one times its area. So 0.00345, 0.009, 0.025, 0.75. That louver is allowing all energy through. All energy that's going through that area. You'll see that that's the weak link in this, and it really dictates the overall transmission loss. But so we have that table that we generated. Now we just have to plug it back into this equation. So we sum up each of these. Then in the denominator, sum up each of these, which would just be 40. You knew it was a 10 by 4 meter wall. That equals this, and then, so that's our composite transmission coefficient. So if we plug that into this equation, we end up getting 17 decibels. So even though this wall here is making up, what is that, like 85% of the, so we have this big concrete wall that produces a transmission loss of 40. It makes up 85% of the wall. But the total, the composite transmission loss is less than half. It's 17 decibels. It's even lower than the door. So these, even though they're small, these ones that allow sound to get through, they're the weak links in the chain. They really dictate what the overall transmission loss is going to be, what the composite transmission loss will be. So we have that here. Transmission loss, the composite transmission loss is heavily dependent on the weakest link. Small gaps or leaks can significantly reduce transmission loss. So here we have this table. It's from Harris, that was the environmental, outdoor sound propagation reading assignment. That's the same author. But he publishes this table. So say you have an STC, remember the sound transmission class. So that's the one that is a single number rating for the transmission loss of an assembly from 125 up to 5,000. So if you had an SDC that produced 50. Remember that that's the minimum required by code between units of multifamily housing, just to give you a subjective impression of SDC 50. But see, you have a leak that is 1% of the total area. It's 1% that would take your 50 STC 50 wall down to 20. And so look up here. I mean, you have some pretty small. Like here is 1,000th of a percent. And even 1,000th of a percent of the total wall area, if you have a leak, that's going to bring your STC down 3 points, 3 decibels, so about 47. So 100th of a percent. So that's 1,000th of a percent. Here's 100th of a percent. It's bringing it down from 50 to maybe like 38. So leaks, small leaks, are really detrimental to your overall sound isolation. So you really need to be careful to eliminate any leaks. I wanted to bring this project up mostly because it's a cool project, but we get to see some details of some of the things we've been talking about. I'm sure most of you are probably familiar with Sonos speakers. They're really widespread and popular right now. I've done quite a few projects with Sonos. The first one I did with them was this store, their New York City flagship store. It's their only dedicated retail space in the US. They put like pop-up stores within other places. Like I did a furniture store in Boston with them, where within the furniture store they set up their speakers and people could buy the speakers there. And I think Target sells their stuff. And actually these pods, these EXR pods, the plan is for these to just start showing up in retail spaces all over the country. The idea, so here we're seeing them in the flagship store in New York City, and they're also just supposed to be showing up in various retail spaces around the country. In both of those situations, they really want you to be able to go into the space and hear their product without all the background noise of a loud, large retail store. And here, where you have multiple of them sitting next to each other, they want people to be able to sit in one and crank it up and not hear it in the other. So sound isolation is really important for them. Say if this is in Target or Best Buy or Fry's Electronics or something like that, then there you just have kind of background retail type noise, which is difficult to isolate a space like this from. But in their New York City store, they wanted to have DJs and bands and stuff like that playing in the store. So sound isolation had to be as good as we can make it. It was limited, as you can see here. There are competing goals, right? They want to be able to see into these spaces. So you can only do so much with glass, with doors, but they want to maximize it. So this is the first pass. Actually, one thing that I really liked about Sonos was they did an entire mock-up of the store in Carson, down in Los Angeles area. So they, before this got built in New York City, they built the entire store within a warehouse in California, and they had people, coming in, and they just would kind of, test out everything on them. And we did multiple versions of each one of these little EXRs and did a lot of testing on them to try to get the sound isolation up as good as possible. But let's talk about some of the details. Here, just you see that New York City store. You see a bunch of them close to each other. These, well, they spell out the letters here. That's going to be important on a slide coming up here. I'll point out something related to that. Before we go on, I really like, this is one of my favorite projects we worked on. I did a lot on this project for acoustics and also designed their AV system, their sound reinforcement system. But they have like multi-million-dollar apartments immediately above this space, and they want to have bands and DJs in there for events. So not only was the isolation of these pods critical, but New York City, as you can imagine, has some pretty detailed, it's not overly strict. I mean, it's pretty typical for the rest of the country, but noise is a little bit more developed. But building code noise ordinance, there were limits of the noise that we could produce in the space above. And this was a furniture store prior to Sonos putting their flagship store in there. And back when it was still a furniture store, I went in there early one morning before they were open. I set up a bunch of speakers. I really got it very loud in there. And I went up into that multi-million-dollar condo above this, and I measured the sound pressure levels up there. And then I had to design the sound isolation. So everything here you see is just, kind of finished materials. We see this slat ceiling, and it has sound absorption up above it. But up above that, we built an entire box. This is a box within a box type of thing. So there's the building shell, and then there's a white box that is hung on spring isolators, and then all the walls are isolated from the building structure with these neoprene mounts. So all the noise in here, it have multiple levels of isolation to get through to the space above, and they're resilient. They're decoupled from each other. But back to within these pods. First, I want to go back to one of the things we worked on a long time ago. This is definitely a space where the room modes could have been an issue, and if I remember it, I think in one of the first designs it was an issue, and then we kind of got them to change the dimensions a little bit to make it better, to get a good distribution of those room modes. So I did this project when I worked for a company, and then once I went into business for myself, I also did, they had a store in London, they had a store in Berlin, they had a store in China. I did all of those. And the London and the Berlin stores, they had lower ceilings than the New York store. So we had to kind of redesign these, and it did shift the modes a little bit, but we ended up getting a solution that worked. But anyways, to some of the other things we've talked about in here. I'm going to get more into the sound isolation and showing some of these details here in a minute. But first, this back wall, that's the glass. So we have this sawtooth. We couldn't really make this absorptive, not effectively absorptive, and didn't want reflections off the back wall. So Sonos's sound, I don't even know what his title is exactly, but Giles Martin, his dad was of Beatles fame. Giles did the Beatles Love album for the Cirque show, and there's another remaster of a bunch of Beatles stuff that came out recently that pretty interesting that he did too. But he was like their sound guy, and everything that I did had to pass his approval. And I didn't even know that he was on the project, but I was in Carson once in this warehouse, and as the mock-up was being built, and he was there, and eventually I realized who he was, but he was actually a really nice guy. But so I should also say he gets most of the credit. Like if you read any of the articles about this project, he gets most of the credit for the acoustics, but I did all the work. But anyways, so had the sawtooth on the back to try to diffuse sound so we don't have reflections coming back. And then we had sawtooth up here, partly, so up here it was sound absorption. You see these kind of felt pads up here. we wanted it sawtooth because they liked the sawtooth look. They wanted to match that on the front, but also by changing the depths of it, we got lower frequency absorption. And then if any high frequency noise or sound would be reflecting off the fabric facing, then it would be diffuse. So that was some of the treatment we did in there. But to the sound isolation details, so that door was, I'm going to talk about the weakest links. That the glass itself is a pretty weak link, but the door is even more so. How I showed you that those gaps are really critical, even 0.001% can be detrimental to your sound isolation. They're, just getting a detail worked out where we got good seals of this highly custom door was a pretty big ordeal. Here we have at the jamb, right, you pull the handle out and it swings like this. So it comes in and presses up against this, and that's adjustable so that we get a good seal there. And then on the bottom, this seal here, this drops down from the bottom of the door. When the door closes, this gets depressed and that drops it down, so it seals. And this is, I'm realizing now that these are actually some earlier details because we ended up incorporating a second seal on all of these. So like when this door would swing shut, not only did it press up against that, but there's also like a neoprene seal that got compressed over here. And on this door, on the bottom, I think maybe we incorporated it right there. And then also the threshold here, that we wanted them to put in one that was smooth, right? You don't want to have all those little dips in it because you want a smooth surface that this will make good contact with. You don't want the sound to like kind of weave its way in and out to make it through. Another weak link was the HVAC. So it brought supply in here and then brought the return out here. So this is you're in the room looking at the front of it. And this is just kind of up along the ceiling line of that front wall. If you're outside of it, there was ductwork that came down. This is all hidden in the New York store. But that hiding it was also part of the acoustics because we have fairly good assembly for all this wall. There's a product called Quiet Rock that was used in here. We tried to get as much mass in there as we could. It did all the things for sound isolation and get a good shell on it. But then we didn't want just 20 gauge sheet metal for the ductwork to be our weak link. So all this was enclosed in something that kind of looked like the wall. And then I pointed out those lights where they spelled out the letters of Sonos on each of the different EXR pods. So this was also an early design. This acrylic, this is where they have these lights behind it, and that's how they would light those up. But so this was like a drawing set that I reviewed. I marked up things and sent it back to the architect. But here we had this weak link, right? There's just this, I forget what this is. It's a synthetic material, but it's only 4 millimeters thick. And we just had this really weak point right here. So I can't remember exactly what we had them do, but we had them, I think, at least like bring this out and overlap it and then beefed up this a little bit. So got rid of that weak link. And then also back here, so they had these cavities where the LED lights were in, and then they just had this open space back here and had them fill that with mass-loaded vinyl. So get a bunch of limp mass in there. So the light boxes themselves were a weak link in the shell of this. And then this was a weak link in the weak link. But by dealing with those, we got it up to where it wasn't too detrimental. Video.
We opened our first retail store here today in New York City, in Soho to be specific. People usually buy Sonos because they've listened to it at a friend's house. It's actually the very best way that you can discover it is by going over and hanging out with a friend and having them show you what it does. So we really wanted to recreate that experience for people who haven't had it before. And we did it by creating a home environment. So there are 7 tiny houses inside of the store. And in each one of them, you can have a demo of Sonos when you go in. I like them because they are these perfect little listening environments. The city is so noisy and crazy and busy, and I think to walk in and to be able to shut the door behind you, block out the world, and really just listen to the music is a wonderful experience. The feedback that we've gotten on the store already has been so surprising. It's amazing what happens when you create an environment like this and see how people really move through it. One of the things that we hadn't expected was to see how interested people are in the design of the space of the room. So people are really interested in the ways in which we've acoustically tuned the rooms, and they're very interested in learning more about how they can design an ideal listening experience in their home. I think what happens when people want to buy something for their home, they often want to touch it and feel it, and when it's a sound system, they really want to hear it. The way to really learn about it and experience it is by doing it in a listening environment. We've created the perfect listening environment here at our new store. We opened our first retail store here today, and
so there were a lot of things in there. She kind of points them out. I wanted to point them out as we went, but I thought I'd just let her talk through it, and then maybe we'll go through it again, and I'll pause it and say a few.
Now, New York City and Soho, to be specific, people usually buy Sonos because they've listened to it at a friend's house. It's actually the very best way that you can.
She's no longer with Sonos. I don't have a whole lot of contact with her, but she's now with Dashlane, and I'm working on their New York City and their Paris offices right now. Everybody that I worked with at Sonos has left, and I'm like some of the guys that I was working with very close on those EXR pods in this store. They've gone into business for themselves, and I'm working on them still. I'm working on projects with them still, but none of them are at Sonos anymore.
Discover it is by going over and hanging out with a friend and having them show you what it does. So we really wanted to recreate that experience for people who haven't had it before, and we did it by.
So this is the back wall, and there's another image of it later. Like I said, I also designed the sound reinforcement system for this space. Obviously they wanted to use all of their own product, so these were Play 3s. They don't offer those anymore. They used to have Play 1, Play 3, and Play 5. They still have the Play 1 and the Play 5, but not the Play 3. But we put those up here, covering most of the retail space. But down at this far end, there's this wall, and it's kind of the back wall of the place. And we didn't want these reflections going down the hall and coming back. So these blocks are like these sort of foam sound absorptive blocks. Most of them are that. Most of them are just sound absorptive. Some of them are really thick, like 8 inches thick or so. But some of them are active speakers. Like here you can see this is an active sub. Essentially these foam blocks are meant to replicate that, but they put actual speakers in here in some places. So some of these Play 3s, so these would be Play 5s, these would be Play 3s, these would be Play 1s. There are some sound bars in there too. I think they're down lower, but the part of it we also, so not all of these were actually, some of them were just there visually. So some of these are purely for sound absorption. Some of them are there just to see the speakers, and some of them are there and actually part of the sound reinforcement system to get even coverage everywhere.
By creating a home environment, so there are 7 tiny houses inside of the store, and in each one of them you can have a demo of Sonos when you go in. I like them because they are these perfect little listening environments. The city is so noisy and crazy and busy, and I think to walk in and to be able to shut the door behind you, block out the world, and really just listen to the music is a wonderful experience. The feedback that we've gotten on the store already has been.
Some of these speakers were active also for the coverage of the room. Most of them were just display.
So surprising. It's amazing what happens when you create an environment like this and see how people really move through it. One of the things that we hadn't expected was
the subs here are active. There's one here and there's one over here.
To see how interested people are in the design of the space of the room.
So here's the perforated panel absorber. This one is not so much the Helmholtz type. This is more the transparency type.
So people are really interested in the ways in which we've acoustically tuned the rooms, and they're very interested in learning more about how they can design an ideal listening experience in their home. I think what happens when people want to buy something for their home, they often want to touch it and feel it, and when it's...
One thing that I'll say to Sonos' credit is in those little listening rooms, their goal was they wanted to make it like a good residential listening space. You know, nothing that is like crazy. You know, they didn't want to put a bunch of stuff in there that the average person wouldn't have. They wanted people to hear what the speakers would sound like in their space when they got home. So we had some things with, you know, like the small, the various aspect ratios and the room modes and reflections off the back wall that we had to deal with. But they didn't want to, like, you know, trick people into thinking it sounds real or making it sound really good in the store, but then, you know, having it sound like crap at home. So I like their outlook on that.
It's a sound system, they really want to hear it. The way to really learn about it and experience it is by doing it in a listening environment. We've created the perfect listening environment here at our new store.
Let's see. I think we have one more video here where you get to hear. If I remember right, this isn't the best recording, but you get to kind of get an idea of what it's like with the store sound and then what it's like just in the room.
So we're doing a story on the store of the future. We're right now in the Soho district of New York City, and we're in the Sonos store. You would not believe how loud the store is because we're in an enclosed listening lounge. And what Sonos has done is they've created this concept of a whole house. So over on this side, they've created the study, could be in the basement. Over here, they've got their kitchen. Over here, they've got their living room. And it allows you to toggle among all of the speakers. But the most magical thing about this is we're in here on our own, and we have a chance to play with the products and actually hear them without any distraction. So I'm just going to pick one of my favorite songs, and I'm going to play now. This is off Spotify. I could have done it on Apple Music, TuneIn Radio.
Please welcome back to the Capitol, the Jerry Garcia Band.
We've got all of the speakers synced as if they were in our house. And we can sit in here and just enjoy the music. That is pretty cool.
So I guess I lied. He doesn't do it with the door open and then close it, but you can hear it's really quiet in there, and he's pretty excited about how loud it is outside and how quiet it is inside. Anyways, let's get back to some equations. So first, transmission loss versus noise reduction. We've been studying transmission loss quite a bit now. I mentioned noise reduction at one point. So transmission loss that's just the ability of a partition to prevent the sound from being transmitted through. Noise reduction is how much the noise is reduced from a source room to a receiver room. And there are, those are actually two pretty similar things. Hopefully you heard the distinction in my description of those, but I've seen professional acoustical consultants that have a fair amount of experience behind them that honestly don't really know the difference between the two of those. So it's a really critical thing. If you spend any time in acoustics, you need to understand the distinction between the two of those. So let's go through the definitions of them again. Here we have transmission loss. It's the inherent property of a partition defining how much sound is blocked from transmitting through, i.e., that is, the sound insulation provided. Noise reduction is the reduction of sound from one space to another. So it's dependent on the transmission loss. It could be very close to the transmission loss. It might be exactly the transmission loss, but there's also these factors of the size of the partition and then the room constant or the absorption of the receiving space. So we're going to look at those, but here we have a source room on the left, we have a receiving room on the right, we have a partition area here in between. And so the area of this partition is important. That's this S. We label this as LP1, we label this as LP2. The room absorption in here is critical. For noise reduction, the volume isn't critical. It's not part of the equation, but the way that this room absorption is obtained is usually by measuring the reverberation time in here, and then using the volume, you calculate the room absorption. So that's why that's shown here. Note these, so this would be like I showed you the pictures of the like the diffusion room, the room to create a diffuse sound field. This would be those types of them. Two of them next to each other. And note they're on springs here. So that idea of we talked about a building needing to be put on springs, not too crazy of an idea. Or I guess maybe all acousticians are crazy. Maybe that's the better conclusion. But let's get to the equation. The book I gave you, I think, is the reading assignment from Fahey. It's a good fundamental, and that's the title of his book. It's a good fundamental grasp of transmission loss, noise reduction. And I don't want to say, obviously that was the one that I picked, so I must think it's good, but he did make a mistake in it. And so maybe if you got to the end, this is like one of the very last pages, you saw that I put this little symbol in here. These should be flipped. So it's 11.126, 126th equation of that chapter. If you made it through all of those, these should have been switched. So instead of that, use this one. Just those two rearranged, everything else is the same. I'm going to explain more about this mistake, but and one thing, books make mistakes. I don't know if we've talked about this in this class or not yet, but don't drink the Kool-Aid. That's like my motto for life. Don't drink the Kool-Aid. I've not that I'm some genius or anything, but I've come across lots of mistakes in books. You've probably observed other mistakes in your other textbooks. It happens. Nobody's perfect. So never just drink the Kool-Aid. Never just think everything's right. Always, it's good to have an understanding of stuff and be able to kind of sift through it and make sure it all makes sense. So S, that's the area of the transmitting partition, and A2, that's the receiving room sound absorption. We saw that from the slides. The absorption would be in Sabins. This is the absorption, or this absorption is determined via reverberation time measurement, like I said on the previous slide. Now, a little bit about, I'm going to have two slides here as to why I'm justifying myself for saying this is wrong. But the insulation of sound provided by the partition, which would be the sound reduction index or the transmission loss, is going to be equal to the reduction of the sound from the source room, LP1, to the receiver room, right? We said that transmission loss is the main component of that. But we also need to make an adjustment due to the influence of the partition size and the receiving room absorption. So if we look at, so we have the loud sound pressure level here, the quieter sound pressure level here. So this minus this, this minus this is going to be a big part of that, or this is going to be a big part of the transmission loss. Let's say that. These other components, say we have a larger surface area, but the sound pressure level in here in the receiving room is the same. That must mean that our transmission loss is greater. So if we have LP1 minus LP2 plus this term, and that's in the numerator, that's going to make that happen. And then the other side of that, if we have, so we have the reduction from room 1 to room 2, which makes sense, is a big part of the transmission loss. But the absorption now, if the absorption in the receiving room is greater, there's more absorption in there, then it's going to reduce the sound in that receiving room. But if the sound pressure level in that second room is still the same, then it must mean that the transmission loss is lower, right? It's letting more sound through if there is more absorption and our sound pressure level in the receiving room is the same. So hopefully that makes sense. I hope I don't screw up this presentation by doing this, but let me bring this up. So here we have the 4 variables, and we have the book equation, and we have the corrected equation. So for one thing, if we're going from 75 to 50, we shouldn't be getting, transmission loss shouldn't be negative, right? It's a transmission loss, so it should be positive. So 75 minus 50, we should be getting something fairly close to 25 for a transmission loss with some adjustments for the square footage and the absorption. The absorption in this case is really low. Like 50 savings is a pretty low number, even for a small space, unless it's like a racquetball court. But let's just look at these variables if we change them a little bit. So right now they're equal. We're getting negative 25, and then it's shifting 6. Shifting this up 6, absolutely. And it's shifting up 6 here from positive 25. So we go from negative 25 plus 6 to 19. Here we go from plus 25 plus 6 to 31. Now, if we increase the area, but the receiving room is the same amount, then let me make sure I say this in the right way. If we increase that area, it means more sound is going to go through, right? Remember the sound intensity, the watts per meter squared, all of that. If we have a bigger area, and that sound pressure level from the source room is the same all over it, we're letting more sound through. But our receiving room sound pressure level is the same. So our transmission loss should be going up then, because we're increasing the sound pressure level through, but what we're experiencing isn't changing. So let's try that. 400, this goes to negative 16. So in absolute terms, it's actually getting smaller. And here goes up to 34. That makes more sense by that reasoning I just gave. And it should be the opposite effect for the absorption because it's in the denominator. And like we said, if there's more sound being absorbed, but the sound pressure level in the receiving room is staying the same, then it must mean that our transmission loss, when we switch to this new condition, must be less. It's letting more sound through, because more is being absorbed, and we're getting the same result. So let's try that. See there, in absolute terms and magnitude, it got larger, but here it gets smaller. So that's what we want. So I hope that all makes sense. I gotta get back to where we were in the slides. And then I just to justify myself, I went and found a couple other books that have this noise reduction equation. So we're going to go through, there's a bunch of different variants of this. Here we have it arranged for transmission loss. We can rearrange it, like if this is the noise reduction, so if we flip this over to this side, then it would be the noise reduction equation. But just to show these are, and that's what this is. So Harris has the noise reduction equation. He takes the source room minus the receiver room equals the transmission loss minus this term. So this matches what I say we should use instead of what the Fahey book says. And then Salter, another big name in acoustics, he wrote a pretty influential book. Kind of more, I think, meant for architects than engineers, but it's still a good book. But he also does it in terms of noise reduction. So he has noise reduction is going to be the source room minus the receiver room. So that's equal to transmission loss. And then note he has plus 10 log A over S. So he moved this over to this side. So we'd have a negative sign here, but he flipped those so the negative sign becomes a positive sign. Right. So these two guys and this equation I'm telling you to use are all consistent. I don't want to take anything away from Fahey. I think the Fahey book was still better than these two books because these two books don't get at all into actually how to calculate the transmission loss for single leaf or how to calculate for double leaf or any of that kind of stuff. So I think this is still a better book for what we're trying to accomplish. He just made one mistake in the equation. But this slide, here we talk about all the different variants of this equation. So if we're trying to use the measurements to determine the transmission loss, this might be what a laboratory would do, or if you're doing it in the field to find out what the transmission loss of a particular assembly is, this is how you would rearrange this equation. If instead you wanted to determine the noise reduction, so you want to know how much is the sound going to be reduced from the source room to the receiver room, then you would use this equation. And if you want to determine the sound pressure level in the receiver room, then you would rearrange it in this way. So receiver room sound pressure level is equal to the source room sound pressure level minus the transmission loss plus this term. So a lot of potential final exam questions could be made from this type of stuff. Hint, hint. Say a little bit more about the noise reduction version of that. So I made a statement that the noise reduction might be exactly the transmission loss, or it might be similar. I just wanted to talk about the effects in a typical space. So it's not really defined more than what a typical space is, but say, just some living space. If the room is fully furnished, like say you have a living room / dining room / kitchen of a condo that's sharing a demise, or on the other side of the demising wall, there's another condo with the exact same thing. If that receiving room is fully finished, so say you have a couch there that has, a couch and an easy chair, and you have carpet and a rug, and you have people's, if you have all this fully furnished absorption within the room, then your noise reduction could exceed the transmission loss by as much as approximately 5 decibels. But if the receiving room is highly reverberant, your noise reduction could be roughly 3 decibels less than the transmission loss. So it just kind of gives you some rules of thumb you could go by. Now, for the determining the sound pressure level in the receiver room version of it. So that receiving room sound pressure level is the sound pressure level experienced in the receiving room. So this is pretty critical for doing any kind of analysis. So LP2 is the sound pressure level experienced in the receiving room at a distance of 75% of the smaller dimension of the transmitting partition. So say you had a 10-foot tall wall that was 30 foot long. Then the smaller partition is 10 feet, or the smaller dimension of the partition is 10 feet, right? The height is smaller than the width. That's 75% of that 10 feet is 7.5 feet. So this LP2, this LP2 would be valid so long as you're within 7.5 feet of that wall. So there are multiple ways of doing this, of finding the sound pressure level at a distance further away. I'm just giving you this one and sticking with this, trying to maybe simplify it, and it is a good method. The thing I wanted to say about this was that, so in all of these, one of the other methods goes into more detail about this, but there's like, think about it in, like when you're close to the wall, it's like a plane wave. As you move a little bit further away, you start to go more into that line source, and then finally it becomes a point source. I'm going to show a picture here. Like, say you have a small mechanical room that's just part of a big. It has a common wall that's a small part of the wall of a much bigger room. If you're right there next to that, it's going to be like it's a plane wave. If this room happens to be quite a bit wider than it is tall, then there'd be a period where it's kind of like a line source. But then if you're way out in a corner of the room, it'd be more of a point source. So that's one of the other methods. It's kind of like we looked at something like that for that when we were looking at the outdoor sound propagation. I'm only saying that at this point because I want you to understand why this is the sound pressure level up to a certain distance away, and then it changes. But we're going to talk about how it changes here in a minute. So just if you're going to do something like this in an indoor sound propagation thing, use this method. Just understand why it's the same for a certain distance away. And then once you go past that, so beyond 75% of the smaller partition dimension, use the relative SPL with distance of interest as ratio compared to 75% of smaller dimension. So in this case, say you were at 15 feet away from the wall, right? We said it's a 10-foot high ceiling, 30 foot wide. So 75% is 7.5 feet. If you're 15 feet away from that area, that wall, then you'd have 15 over 7.5. That's what's meant here by this. Use relative SPL with distance of interest. So that would be our 15 feet as a ratio compared to 75% of the smaller dimension. That would be our 7.5 feet. So it'd be 2. Now, hopefully you remember this relative SPL thing. So you have equations to do this, right? You can do it with an equation, but we also have this table. So depending on however much absorption there is in that receiving room, then in that case would be somewhere along this line. So if we just had 50 Sabins of absorption, we'd be here at 100. So 50 Sabins, then if we were twice as far away from it, basically there'd be no reduction. But if we had 100, then we'd be maybe like 2 decibels reduction at 15 feet. If we had 200, we'd be at maybe 4 decibels reduction at 15 feet. Hopefully that's clear. I wanted to just show a little bit of my chicken scratch here to talk through a couple of examples of what you would actually consider to be your your area, and how you'd go about attacking problems like these. I kind of alluded to this just a few minutes ago in my description of the larger room where so say you have a lab for a company designing robots. It's a big room, and then they have this mechanical room up here. They have a hydraulic power unit in this space. So it's a reverberant space. The sound pressure level throughout here is going to be pretty similar. It's the same over this entire wall. So you would intake, this would be your S in that equation for your noise reduction. So you'd have your sound pressure level in the receiver room, in the source room, your LP1. So say you're trying to find LP2, that's some point out here. Whatever your absorption for this space would be, you could determine that if it's existing with the reverberation time measurement and use the volume of the space in the equation, or you could predict it just on what the materials are going to be when they go in there. But you get that area, the absorption of the space, and the distance. If you're right up here, the distance isn't going to matter, right? If you're within 75% of this dimension, the distance isn't going to matter. But if you are out here, it is going to matter. Whatever the ratio of this distance to 75% of this is, then you use that relative SPL to make a further reduction for what you get from your noise reduction for this point out here. Now, say we have an auditorium and we have like a packaged rooftop unit on top. You wouldn't want to do that. If you have an auditorium, don't put that on top. It happens sometimes. Say you did, or you're trying. Say more that the the architect wants to put that there, or a mechanical engineer wants to put that there, and you're trying to convince them that they shouldn't do that. You're trying to calculate what the sound pressure level is going to be down here in the seating in auditorium. Now you don't, in this case, you don't want to use the entire area of the roof. Hopefully my chicken scratch here we're showing, it's a chiller on the roof. I cut that off. It's not root. My son walked in here a few minutes ago and was actually giving me a hard time about this. So I'm trying to explain all of my poor writing. But this is roof. So the chiller on roof, infinity absorption. It's outside, right? We have absorption to all of the universe. And like I said, you do not use the total roof area. Because you have total absorption, you're going to have a very different sound pressure level if you're here, 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 right? So what I would do in this case, I divide it up into zones. I just pick an area. You should know now that if you see you model this as a point source, and as you double your distance from it, you lose minus 6 decibels with each doubling of distance. So we're going to get a really quick drop off in a short amount of distance, and then as we move further away, we're not going to get that much drop off. So you might want to have one zone here that's say just like 3 feet. So you have an area. So say this is like 5 by 9 feet. So you might want to take an area that is 3, 9, 3, so 15, and then 3, 5, 3, 11. So you want to have an 11 by 19 area, and you have a sound pressure level for what the average distance of this area is. And then maybe you want to do another zone out here where it's the area of this minus the area of this. Like maybe instead of having your 3-foot buffer now, maybe you want to go out to like a 6-foot buffer or something like that. But so this area will be this area minus this, and then you're going to have a distance that's the average distance to this zone to find your sound pressure level of your, we'll call the outdoors your source room. Now, in a lot of cases, I end up just kind of making one estimate like this. And in the more critical ones, I'll go out to 2. I haven't had a whole lot of cases where I've ever really felt it was justified to go beyond a couple zones. But the main thing is just don't do the sound pressure level of the entire area. If you do that, you might get, so you have a source, you have a sound pressure level out here. You could potentially, if you had a big enough area, you could potentially get a sound pressure level on the inside that is larger than the sound pressure level outside. You know that's not possible, right? But I've seen people make calculations like that. So you don't want to do that. Make a more reasonable approximation like this. If it's really critical, then do kind of like a finite elemental analysis type of thing. That's it. See you later.